All right. Okay, let's make a start. So welcome everyone to day 4 and to the testing workshop. So this is something close to my heart. I've spent probably 2 decades or so thinking about how do we ensure that software does what we intend it to do. And there are lots of ways of approaching that and ensuring that. And one way, which is probably one of the most commonly deployed techniques, is testing. It's something that we're always trying to bring into all of the projects we do, if it's not already there, and something that can have a big effect on the quality of our research software. So it's close to our hearts. So we thought it's really important to have some time at the summer school to talk about it. So I like to start quite high level when thinking about this and think about the concept of validation versus verification. Often in common English usage, these two things get smushed together, and we kind of talk about validating models or verifying models, and those words can kind of mean the same thing to us sometimes. But actually, there's been quite a lot written trying to actually tease them apart and distinguish the idea that validation is really a kind of a scientific question. It's, did we implement the right equations? Are we really modeling the world accurately? Do we have a good model representation of it? Whereas verification is, did we implement the equations right? Did we actually do the thing that we intended to do? We might have some kind of mathematical model in our head, some PDEs, some ODEs, something like that, and we're discretizing down and we're making an implementation. But does the implementation actually give a faithful representation of our equations? So did we implement the right equations versus did we implement the equations right? And if you've got some code, some model, or some data analysis, and it does the wrong thing, then teasing these two things apart can be difficult, especially if you're in a context where you're still trying to understand the science. So actually trying to separate these things out is difficult. And if you haven't done any sort of work on the verification side for your software, then it's even more difficult. So that's what we're going to be thinking about today. When we talk about verified software or verifying software, we have to think about with respect to what. It's always with respect to some kind of specification. That specification might be, I don't want my program to crash. I don't want it to throw an exception. I don't want it to get some sort of memory error or something like that. That's a kind of very common specification that most people can agree on. And there are tools out there like static analysis tools that might automatically try and find these kind of mistakes. But we might have other specifications in mind that come from our scientific domain. So essentially the whole umbrella approach of program verification, which is like a very, very large area, is some kind of procedures where you take an implementation and you check it against a specification in some way. Now, sometimes we might do that, and we're the person who's this kind of check procedure, like, eyeballing the plots, right? You run the thing, you look at the plots, and you say, oh, yeah, that looks about right. And is that a verification or a validation? It gets a bit blurry. So the important thing about the specifications is that we can sort of make arbitrarily complex specifications. We can specify and specify software. At the end of the day, our specifications could also be wrong as well. So there's some kind of higher level thinking we have to do about our specifications. The kind of specs that we want depends on our goals and values, and also which risks we're trying to guard against in our code. We can't guard against all kinds of bugs. And there are various projects out in the world, a lot of kind of from the computer science side, things like there's SEL4 kernel, which is a formally verified operating system kernel, where they've worked really hard to specify how should an operating system kernel behave. They use lots of formal method techniques to prove that it does that thing. Or there's the Concert C compiler. It's a verified C compiler. So they have a formalized subset of the C language, and they formally mathematically verify that the C compiler preserves the meaning across all of its translation steps. But those are like massively huge efforts that take really just tens and tens and tens of computer scientists, years and years and years. And we don't really have the time to do that. And there's kind of risks there that people are trying to guard against in like the C compilers and the kernels that perhaps we don't need to worry about. Here, we're just trying to bring some level of correctness checking to our software, which is going to help us have increased confidence in our code and also speed up the work that we're doing. I think too often, and I'm also guilty of this, we can use validation as a proxy for verification. So kind of doing a scientific test, and if it looks good scientifically, then saying, the code must be right. You know, like, can we get a stable run? Does it kind of conserve some properties, or does it seem plausible physically? Can we even reproduce some observational data or something from the historical record? We might use these as kind of tests of our code. And if it does these things, we think great. But if it doesn't, if something like this fails, if we can't reproduce observational data, then we're stuck in this problem of trying to tease apart validation and verification. If it sort of just doesn't work and doesn't behave as we think, well, did we get the science wrong, or did we get the code wrong, or maybe both? I mean, in my experience, probably both. But even if you think, okay, the science is settled, we know what we're doing here, we've got the right kind of model, but if the scientific tests sort of don't pass, then we don't have very good locality trying to understand where actually are the bugs. That we know that there is some kind of bugs, but the error localization is poor. It doesn't tell us where in our code we went wrong. So part of what we're doing today in testing is also about trying to break things down so we can find out if there are bugs in our code, where are they, so that we can diagnose them and fix them more easily and more quickly. So that's the high level idea. There are a huge number of techniques that come under the umbrella of verification. As I said, we're going to focus on testing. The nice thing about testing is that the specification language is typically the same as the implementation language that you're already doing. So if you're writing some Python code, you're going to write some tests, and they're also written in Python. So you're providing some kind of specification of your problem, but it's in the same language. So you don't have to go and learn some fancy other tools and some formal logic tools or some proof language or something like that. We're within something that's already familiar to us. And what we're going to see, we've got 2 sessions today. I'll kind of explain a bit how those are going to fall out. But one of the kind of key ideas is that we're going to take our functions and test them on some subset of the inputs. Now, there's been lots of discussion about testing as a kind of an overall verification technique. A famous computer scientist, Edgar Dijkstra, was a little bit critical of it. And he said, well, it's okay, but it doesn't show the absence of bugs. It doesn't guarantee us that there aren't bugs in our code. Which is true. We might not be able to test everything. There might be things that we never thought of to test that are lurking there in our code. So we should understand the limitations of tests at the beginning. They're very useful and they're very important. We should all do them, but it doesn't guarantee that there aren't bugs still in our code. Where I think Dijkstra gets it wrong is that it does actually show us the presence of some bugs, though. It might not show us the absence of bugs in general, but typically it does show us the presence of bugs that do exist, and it helps us to cut them out. And then it provides a bunch of other benefits as well along the way. So the kind of key principles of the next 2 sessions is we're going to do testing, and we're going to do it in an automated way. We don't want to have to be doing some manual procedures every time we want to test our code. We don't want to be running something and eyeballing a plot because, well, we might just miss something. It's not very high fidelity. So we want some sort of automated procedures. That's one of the main things we're going to do. The goal is that this is going to help us speed up our development because we reduce the amount of time we spend hunting for bugs. We've all probably spent time trying to work out why our code doesn't work. This is going to reduce some of that time. We're going to catch things early so that we're not then somewhere down the line in our project trying to find bugs when we're trying to do some big runs on something. It increases confidence in our code. And then when we want to do things later on, like say we want to refactor our code to make it easier to understand, or to reuse bits of our code base to make it more modular, or maybe we want to improve the performance of our code, when we have the good testing in place, it gives us some confidence that we're not changing the code while we're doing that refactoring. So when lots of projects that we've done in the past, we sort of involved in, okay, let's make this piece of code faster. The first thing is, okay, are they good tests? So that we make sure that when we're making it faster, we also don't change how it behaves. So it's about this preserving the meaning, this semantic preservation. So these are the kind of principles we'll be thinking about. So the plan is that we're going to use Python and PyTest. A lot of these ideas carry over into other languages. A lot of what I'll be saying, there'll be some analog in your language of choice. You just have to find the relevant test frameworks and work out how it's done in that language. But we'll use Python as our kind of example language today, because I think we're all pretty familiar with Python and it's being used in lots of the other courses. We're going to have a few parts. We're going to look at 4 different kinds of testing. Today, in this morning session, we're going to focus mostly on these 2, smoke tests and unit tests. The second part, the second session, will have integration and property-based tests. This is super exciting and cool. Hopefully, I'll say a little bit about it at the end before we finish. I will do live demos. So you can go to the repo here and find the code that I'm using. The idea in this session is it's going to be more of a kind of code along. So you don't have to, but you can get hold of the code and you can sort of do the same things that I'm doing as I go. You might like to do that. If someone could pop that on the Slack, that'd be appreciated. Great, thank you. But okay, so how does this break down into the 2 sessions? So the first session is going to be a little bit more lecture-y, sorry. So that's going to be me talking and doing demos. Session 2, we're going to actually have some time to try exercises. So you'll see there's an exercise sheet on the repository with a bunch of questions, a bunch of tasks for you to do. And in the second session, we'll start with just doing exercises and me and Isaac kind of going around and helping. Then we'll do a little bit more lecture talking about integration and property-based tests. And then we'll go back to doing some exercises. And if you don't come to the second session, that's fine. Go and check out the stuff later. And you can try out the exercises on your own time and ask us any questions if you need to on the Slack or over email. So let's just pop over to the code for a second. So in the repository, actually I'll go over here, you'll see we've got this example directory. That's some code, some really basic sort of 0-dimensional energy balance model that I've written some tests for. That's under example. You can see the exercises in there as well, and the slides are linked here. So we're going to be in here for a bit, and the way that the code is organized is there's a source folder, which is the source code for the actual sort of the actual program, and then there's tests. That's where all the tests are going to live. And then there's some top-level bits and bobs here, things like the requirements file. This is a configuration file that's used by the source code, and so on. So we're going to be kind of jumping back a little bit between the source code. I'll occasionally look at that, and the testing directory in there, where we've got tests. So the way that PyTest organizes things is that we put our tests in .py files. We're writing them as Python code in some directory that's typically called tests. And each test, well, we have files in there, Python files, which we can, I think we've got 5 or 6 in here, which are groups of different tests, testing different modules. And we write test groups as functions, which start with the name, the symbol test underscore, so this prefix. And then we use the assert keyword in Python as a way of describing some kind of Boolean expression, some property that we want to be true. And so this is our test. The test framework will pick this up and count whether this has indeed been true or false, and tell us when it's false and when it fails. So the first tiny little demo, which is not using any of the code actually in the energy balance model, is in demo.py. See, I've written a function here which does something nice and straightforward, x+1, and I have a test here. So we know it's a test because it says test underscore, and it uses the assert keyword followed by a Boolean expression, and it says we want to check that func applied to 3 is equal to 4. So the way I can run this now is with PyTest, demo.py, and the test, we get a little report telling us that 1 test has passed. So it's found that there's 1 test, it ran that, the assert statement was true, so it passes. And if I did something else, maybe I changed the function like this and run it again, okay, now we see that the test fails and we get some information about that. It's filled in here in the error message, what the actual answer produced was 5, and we were expecting it to equal 4, so that fails. We see that we've got this sort of the actual versus expected doesn't match. And so I might put in some other tests as well, and I can put several in there. It's sort of seen as the same test group, but if either one of these things fail, then the overall test fails. So if I put in here, do like that, we see we've got one thing failing. So it is usually better to split out the asserts into different tests. It sort of depends. It's a bit of a design choice about how you want to put these things together. But for the moment, I'll put these kind of simple tests in like that for my function. Okay, so I'll just give you a moment if you're kind of poking things yourself. I know there probably needed to be some setup where you cloned and install things. I'll just give you 30 seconds if you're trying things out. Okay, so we've been using this assert keyword. It's part of the Python syntax. This is not something that's sort of specific to PyTest. You can write this in normal code. And if you do assert with some Boolean expression and it gets executed and it's false, then it causes an exception to happen in normal Python code. You can also write it like this, where you have a Boolean expression, comma, and then a string. The idea is that it's executed, and if this thing is false, then this string is output with some kind of more helpful message, perhaps, to explain what's happened and why. So I think there might be a couple of tests I put in where I put this extra string expression, which includes a bit more information, so that when the test is failing, I can sort of see something more about what's going on. So that's a common approach. So that's some entry kind of basics. Let's talk about the idea of a smoke test. So smoke tests are simply about checking whether your code catches fire or not. Did it actually sort of start up without bursting into flames? Sometime last year, I was digging around in my loft, in my attic, and I found my old BBC Micro. I plugged it in. I failed the smoke test. All of the magic smoke escaped, which was very sad. So I couldn't show it to my kids because some capacitor blew in it or something. So a smoke test is something that's going to check sort of tends to be typical things like, were we able to load the module for this particular program that we're testing? Were we able to run its initialization functions? So in the test directory, I've got smoke test. Let's look at the very first one here. We can, just move this out of the way. You can see there's this test initialization at the top. And what it does is it imports my energy balance package. It imports the init at the top level, and then it checks whether that's none or not. So if there was, I don't know, something had gone wrong with the overall package setup or my overall kind of build system, then importing would fail, and this would give me a none value. And so this is basically checking, can we import things? Can we import our program, which is called energy balance? Another smoke test might be if there's some kind of configuration files that have to be loaded in, or like name lists, or I don't know, something like this. You might want to check that that also works at the beginning, because other tests are going to depend on it. So in the case of this energy balance code, what it does is it reads in, just pop the code open. It has this, don't need to read all of this, but it has this initialize module in it, which loads a parameter file, a YAML file, which contains some sort of constants that you want to read in for this. So you could be switching between modeling different planets. So it reads that in here, and we need to check that that actually works. So so this smoke test imports the package, and it runs the init function, which does this loading up of the configuration file. And then it checks whether one of the global variables that it initializes, it checks that it's not null. So if I don't know, if this file didn't exist or something went wrong, then it would be none. Or this would throw an exception, which would then mean this doesn't run. So this is checking just basic initialization. So again, I can run this. And there's some warnings here to do with some other smoke tests, which I have down here, which are to do with checking whether plots actually get run. I'm not going to go into this. You can look at this in your own time. But this is using what's called a headless version of matplotlib, where it sort of generates matplotlib plots, but it actually just doesn't show them to us. But it checks basically, can the plots be generated? It doesn't care what's in them. It's just were they able to run. But I won't get into that. That's something to look at later, but that's also one of the smoke tests in here. So we see great, 3 tests have passed. So we know that the thing is not going to catch fire on somebody who's running it. So this is just a basic kind of initial thing to do. And there's that example down there, just on the slide, repeated. Okay, so we don't need to spend too much time on that. Don't typically need a lot of smoke tests. It's just basic checking that things can load up okay. Now, unit tests is where we're going to spend a bit more time. This is one of the sort of key kind of techniques. The idea of a unit is that a unit is just some sort of smaller piece of code. We want to test the behavior of some particular small bit of our code base. Now, this kind of implies that we have our code base structured in a way such that we are able to test the smaller parts. So the kind of unit testing technique goes hand in hand with making modular code. If we break it down into smaller bits, it's easier to document, it's easier for people to understand, it's easier to test, it's easier to change bits, it's easier to reuse. So this really goes hand in hand with code modularization. So the idea is we want to run a little unit of code, say some smaller function, and compare its actual results with its expected results. So that's like we had in that first demo example. So as another example, let's say we've written some kind of function on floats. This is just an abstract way of me writing its signature. It's the square function. It takes in a float and gives back a float. We might think of some tests that we want this to pass, like square of 2 equals to 4. Let's do that again. Yeah, we want this to pass because we know we have some idea about how the square function should work. But how do we think about what would be useful input-output cases to test? Well, one approach is for us to go kind of systematically and think, well, what are the sort of simpler cases that should hold for this piece of code? So what are the kind of simplest examples I can think of based on this input domain? So I might start with 0 and 1. Okay, square of 0 should be equal to 0, square of 1 should be equal to 1. Let's move up to something a bit fancier, like square of 4 equals 16. That's a good one because maybe square of 2 could just be multiplying by 2 in that case. I don't know. So let's try something a little bit more complex. And once you've moved, okay, negative numbers, how does that behave? So you sort of start with the simple base cases, move to complex, and then start trying to think, what are some corner cases? What are some sort of unusual inputs that might be possible for this function? So maybe I can ask the audience then. So if you've got a function that takes in a floating point number, what would be some corner cases that I might want to check the behavior of? Corner cases in the floating point data type.
Like errors.
Well, yeah, one at a time. So Charlie.
Like a really small number, so that when you square it, it doesn't represent correctly.
Yeah, that's a great example. Yeah, like a really small, like a machine epsilon number. Yeah.
Rounding errors.
Rounding errors. Okay, so that's related to small things. Yeah. Infinity. Yes. Yeah, that's a good one. So floating point has a representation of infinity, and that can have slightly odd behavior. There's one more. Nan, yes, that's one I've got on the slide. I didn't put all of them. So nan, which means not a number. It's a value within floating point, and it has some slightly odd behaviors and can do strange things to your code. So that might be something you want to guard against. Maybe actually you don't care. Again, as I said, the value of your specification is what you make it. Maybe you don't care whether people put nans in, you don't care what happens, but maybe you want to check, well, how does things behave when we put in this not a number nan. And typically nan, if you do nan plus something else, the answer is nan. And if you do nan times something else, the answer is nan. So it kind of propagates through all of your code and yeah, goes everywhere. So just on the slide here, what I've done now is codify those ideas into a test, which puts a bunch of those together, maybe slightly different here. An interesting thing about nan is that nan is not equal to itself. So this kind of destroys our usual behavior of equality. We usually think of equality as being reflexive, so x is equal to x, but that's not the case with nan. Nan is not equal to nan, which is always a source of frustration. So I couldn't do square of nan equals nan. Instead, I have to use this is nan function, which checks whether it's a nan or not. So there's a slight interesting thing there to think about with floating point. I will mention some other things. We've had people talking about rounding. I'll mention that again in a moment. So in test helpers, the square function is in helpers, so we're importing that. I imported the nan value from math and is nan. We have this range of tests which goes kind of systematically, a bit more complex, and then corner case. So you can see that there. Let's check. Go on, I might as well run it. Here it is. So I can run that individual test. That I can run all of the tests that are in this whole folder by just doing this, which I guess I'll do. I'm not sure. Oh yeah, they all pass. Okay, so there's a whole bunch of tests. That's running everything in that folder there, which we'll see over the 2 sessions. All right, I'll just pause for a second. Any questions? Yes.
I could probably answer this question by looking at the code myself, but the tests you got there are squaring integers, and you made it. You asked this question about floating point numbers.
Yeah.
How should we compare floating point numbers and tests?
Yes. So Chris points out that all of the examples I've chosen so far are actually whole numbers. They're actually the integer subset of floating point. Which maybe then means this isn't a great test. I should also be thinking about some things that actually test that behavior of floating point. But Chris raised, how do we deal with the rounding errors that exist in floating point? So quick bit of background. Floating point is an approximate representation of the real numbers. It is not the real numbers. So not every single real number is represented in there. There's some approximation. So there are some things that basically just don't exist that you can't represent, like 1/3, for example. You can't represent that exactly. It's instead it's 0.33333, but then it gets truncated. It's finite representation. So this and this, one of the implications of this is that it destroys a lot of nice mathematical properties for us. So addition and multiplication, we typically think of that in the real number space in our heads in maths, they are associative. So if we're doing a times b times c, it doesn't matter how we group those operations. We can do a times b and then times c afterwards, or we can do the b times c first and then times a. But in floating point, that's not the case. If you reassociate, you can get different answers, which is then a source of like non-determinism when you've got parallel code where things get reassociated because of different scheduling choices. So it's a great source of fun. So we can deal with that. When am I going? Oh, I'm going to deal with it now. Great. Good. I'm glad it was there. So one of the ways we can deal with this, there's a whole bunch of different ways. So PyTest itself provides this prox constructor. Let's see if we've got an example. I think I do. Okay, so let's go down now to some of these functions. So perhaps I'll just work through a few of these for a second before we get to that particular one. So the energy balance code, it has a lot of the standard things you'd have in a energy balance model. We have this function energy in, which treats the planet as a black body radiator, but we specify its albedo. So we what do we do? We specify we specify the fraction of solar energy, and we get a floating point out, which is how much is going to kind of be sucked into this black body in joules per second. So a test that I thought of here, this was kind of systematically specializing, is to think, well, what happens when the albedo is 1? What happens when it's maximally reflective? The energy in should be 0 then, because everything is being reflected back out. So I could kind of come up with this specification without having to do any calculations or look at the code. This is what we call like an extremal value. There's a kind of nice property to it. So this is something I wanted to check. When the albedo is 1, I shouldn't be actually absorbing energy in here. Then I put another test in. I thought, okay, what about when it's 0? Well, okay, then what I'm doing here is a little bit boring. In a sense, I'm kind of replicating the calculation of the code, right? I'm taking the solar constant, I'm multiplying it by the surface area. I'm just saying it's, it's all of the energy. So that's perhaps not the most exciting in a sense, because I'm having to do that. We're going to come back to this one. Let's see. Okay, so I think I had an example here where I needed to do a prox. So what I did here was I actually ran this code, and I basically I ran it with some particular inputs, and I got that output and I turned it into a test. And this is like a technique that's sometimes useful. Maybe you've already written the code, but you want to put some things in later so that when you're doing some later refactoring, you can check that the behavior is the same. So you're kind of codifying some of how it behaves now in a test. So what I did was I went in and I imported energy balance. Where am I? I should set my Python path, sorry. This is probably in the exercise instructions. This will help you. So if you're doing this later, you might want to set your Python path. There we go. You pass me. Right, so what was I doing? Python 3. Actually, let's do 3.11. Great. So I know I've got to run the init function, and then okay, so this is another function that's about the emissivity of Earth, and I think this is albedo and temperature. So I stuck some values in. Sorry, can't type. And I got a big floating point number out. And so I could codify this in my tests, but what I've done here is use the PyTest approximate. So what this has enabled me to do is to put a number in and say, I want this thing to be approximately equal to this thing up to an absolute tolerance of 1 times 10 to the minus 4. So this parameter here is saying, what's the tolerance? How much am I allowed to vary plus or minus? And this is an absolute tolerance, so it is really plus or minus on this thing here. So if I make this a tighter bound, let's run this test. Now we fail, and we see we've got this nice error here saying, well, the thing that we actually got was this. We were trying to compare it against 0.61 blah, 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 plus or minus times 10 to the minus 10. That was too fine-grained. Okay, I could have put a more exact value in here, but I wanted to demo this. You can also change this to relative error as well. So you can specify the relative error. That's the kind of, what is it? It's, I've forgotten the calculation now. It's the difference between them divided by the minimum. The difference between them divided by one of them. With relative error, this is good when things are going to be kind of a similar, let's think, I've forgotten this now, a similar kind of magnitude, but absolute error is good if things could be sort of far apart. I've got slides on that, that's good. So relative tolerance is good when we've got a similar scale, when things are sort of close together. Absolute tolerance catches small things where things are kind of further apart. in terms of their magnitude. So you can do it this way by doing this kind of creating this approximate number object to do this comparison. There are also within NumPy some functions for doing this. There's sort of is close, which is again this is a Boolean test. You put in some number, say is one thing, is it close to the other, and it's doing the same kind of idea. And you can also do it across arrays as well with NumPy all close. So this is useful when maybe you're going to compare two things which might have slightly different calculations or might end up with slightly different associations, or maybe you have a process where there is some parallelism and the numbers do slightly change each time because of this scheduling, meaning that floating point gets reassociated. So you can't tell exactly what it's going to be. So you want to do some approximation here. So that's the way to deal with that in your tests. And yeah, this exists in other platforms as well. You just have to find what's your way of doing approximate testing. You can do the calculation manually yourself as well, if you need to. Okay. So I'm going to move on to a different context now, concept, which is test parameterization. So we saw with this thing, we had to like repeat ourselves a lot, input output, running the function over and over again. We can make a parameterized test where we basically suck out all of this input output information into a little data structure and say, here's a set of input output pairs, run this bit of code with all of those different pairs. So this is how we do this in PyTest. So it's a way of us simplifying a bit our test. So we've got this PyTest mark parameterized, this decorator here that says, okay, what we're going to have this list of pairs, and this is going to be called the value and the expected. So we're just extracting all of these possibilities here, giving them in a list. And then we just have to do this test once. And so what PyTest is going to do is run this function on every single one of these input output pairs. So it's kind of simplifying your code so you don't have to kind of repeat the logic, just codifying that in a data structure. And so it makes it easier then to just add more examples to this list. Yes?
Should you keep all your tests in the tree forever?
Yeah, I think so. Because then it will enable people to run them and have some confidence in your code. It will enable you to run them later if you're changing things and make sure nothing's changed. I think it's often we need them a lot when we're developing, and maybe if we get to a point where we're saying, well, I'm never going to change this code again, it's still useful for people to be able to run them and have some confidence. But I think it's rare that you get to a point where software is not changing at some point. So it will give you confidence if you're changing something down the line. Since we've talked a bunch about generative AI so far this summer school, I guess we could see, okay, so we've got test helpers parameters. I guess we could see maybe whether Copilot can generate us some more tests, which is can often do. Okay, -3 and 9. Ah, no, Copilot, you've fallen into the NaN trap. Go on, let's see what these do. I think these mostly look fine. Okay, that's that. I'll think that's enough. NaN equals NaN. Come on. Right. So unfortunately, Copilot's screwed that one up. So we'll take that one out. But this one's interesting. We've got a floating point issue here, right? We've got 0.01. Where is this coming from? It's coming from here, right? 0.1 squared should be 0.01. And we're seeing good old floating point issue. We've got coming out of it, we've got 0.01, so I should probably change this test to deal with that and add in the approximation. And it's completed that for me. Absolute tolerance of 1. Yeah, this is kind of a standard. Maybe I think we should be able to do it much smaller than that. Okay, so now things are good. So my experience is that using something like Copilot can be quite good for generating more tests. It can be good for writing entire tests. but you've got to test your tests. And you've got to think about it. And sometimes, as we just saw, it will do things which are not good tests. I'm going to turn it off because otherwise it's going to get really annoying. Right. So that was test parameterization by this kind of decorator structure here. Don't have to memorize it. I often forget what it looks like and have to look it up in my own code. Probably Copilot can generate that kind of thing for you quite nicely as well. All right, another idea is test fixtures. And actually, this was sneaked into one of the things I already showed you. Sometimes when we're running our tests, we want to actually provide some kind of context to them before they're run. So in this code, we have this init function for our energy balance model that reads in from parameters.yaml. So before we use it, we have to do initialize, and it's kind of annoying to have to write that everywhere in our code. You'll notice that actually I didn't in test helpers, test energy balance. I was running all of these things here, like the energy in checks, but I wasn't running the init function. And that's because I was using a fixture, which does that ahead of time for us. So that the PyTest sort of standard thing is to have this top level file called conftest.py, where you can specify a bunch of things that are going to be used by the rest of your tests. It's a sort of top level module of helpers for your tests. And this decorator here is defining this as a fixture, which is something that can get sort of run automatically for us. I'm calling it setup, and okay, it doesn't do anything that fancy. It runs energy balance in it. And how do I use this? So in my tests, I don't need to import this explicitly, conftest, because PyTest does that for me. But what I do is I mention the name of that fixture as a parameter, to the function. So I don't actually have to do anything with that because I don't actually need the results of it. If I needed the results, I could sort of refer to setup. Maybe this generated something I needed to check. But in this case, this means this just gets run for me. It runs that setup function at the start before the test. And so we've got the initialize happening, and I can just go ahead and do my check here. So as you get fancier and fancier into doing testing, you might start getting really fancy fixtures that do different things for you. We had an interesting project that Isaac was working on with me, where we were testing we were translating a code base from MATLAB to Python. Some of you might have seen the poster on Tuesday, and we wanted to be able to test both the MATLAB and the Python code. So we wrote just one set of tests in Python, but we had the MATLAB code sort of hooked into the Python so that we could test the MATLAB from the Python and the Python from the Python. And we did it via a fixture and switched over the runtime underneath between the two things. And that we had to do a whole load of other stuff in there about how does data get handled and things like that. But it meant we could just write one set of tests and have a fixture that we then switched in the back end to say, okay, test the MATLAB code, now test the Python. So that went into a bunch of fancy stuff that we did in conftest. So I can put a link to that if you want to see. It gets quite complicated, but this ends up being quite useful in these kind of situations where there's something you want to do ahead of time that's going to set your tests up. So you can see all of these things in test energy balance. They're using setup here. We don't actually need to get the result, but this is triggering that running of that function for us. So sometimes we want to check that things fail. I call this a negative test. Guess this is standard terminology, but I feel like I might have invented it. We want this thing to fail, and we need to catch that kind of failure. So a good example might be if I stick in a negative albedo, doesn't really make sense in this context, and I want to check that this is ignored by energy in and that it throws an exception. So I'm sort of expecting that this is something that's out of range, and I want to make sure that my energy in function is checking for these kind of things and actually complaining if it gets a negative value. I don't want to get like negative energy. I mean, you could come up with a physical meaning for that in this case. It's just going in a different direction, right? But I've decided that I want to just have my albedo be between 0 and 1 inclusive, and anything negative we want to kind of report back as an error. So this is a way to do that. I've set the albedo. I've said, okay, albedo is minus 0.1, and I'm running energy balance. And then I have this with context thing going on here, which basically is expecting this to then raise the value error. So, which it does, so that test passed. Let's see what happens if I change it. So this was in energy balance. Everything's fine. If I go and change that code now, just split. So you can see in the code that I have this check at the beginning that checks the albedo. Let's say I just took that away. Let's run this again. Now we get this test failing, and it's saying, well, I ran it, but it did not raise the value error down here. So it's down at the bottom. So we've got a negative test, which is checking this exceptional behavior. So we could put more of those in. This is not an exhaustive test suite, but just giving you some examples. So our kind of general principle when we're writing these unit tests is we want to kind of cover a representative sample of the space. And we're never going to be able to cover it all. I mean, it's already, probably most of your input domains are actually going to be infinite. Floating point isn't infinite, but it's very large. But you want to get something that's representative. So start with that kind of systematic. Think of the complex cases, think of some corner cases. If you're testing things that involve data structures, then you might want to think about, well, how does it behave with an empty data structure? Maybe it's a function on lists. What happens if I give it the empty list? Or something small with just one value? Or maybe you've got something with binary trees and you want to say, okay, what are all the possible kind of shapes that I could have? Maybe I want to check the empty tree, or a left-leaning tree, or a right-leaning tree. Or what are all the ways I can construct, like what are the different constructors I have for this data type? I should check all of those and check how it behaves on every construction. And another question you might ask is, what happens if I have a very, very large data structure? Is something bad going to happen? Do I actually want to guard against that in my code and say, no, please don't give me a list that has more than 2 to the 32 elements in it, or something like that, because I'm going to struggle to do things with it. So those are kind of some general principles. So there's a kind of approach to testing that's from the software engineering literature that's called test-driven development. In that approach, the idea is that you start by writing tests. You specify first and you implement second. And there are lots of kind of versions of something-driven development out there. Someone I know likes to do talk-driven development, where they, make this, when they book in a talk to give a talk somewhere, and that's when they work on their software in the week before they give their talk. So they do talk-driven development. Test-driven development, we're going to specify first. So we actually write tests before we write any other code. And there are kind of variants of this. The real, the kind of classic TDD is a very tight loop. So you start by writing a single test, and then you write just enough code to make the test pass. And then maybe you do a bit of refactoring, then you write another test. And then you do just enough to make that pass, and so on. I have my opinions about that. I think that maybe it's better to do something where you actually do more kind of failing tests first. Oh, I thought I had that on the slide. So maybe you write a few tests and then write a bit more code here and then check it. It doesn't have to just be one-to-one. Oh yeah, one could be repeated first. You could write a whole bunch of tests before writing your code, but the general idea is the same. You're trying to force yourself to think first, how do I expect this to behave? And then that will go into then how you actually design the software. It's kind of forcing you to slow down, I think, in some ways, not just, I'm going to go start hacking code. Think, no, how should this thing actually function? And it also encourages you into a more modular design, because if you're thinking, oh, I need to unit test this code, I've written the unit tests, you're already thinking about what's that kind of glob of code going to be, what's its parameters going to be, what's its interface, how big is it? It already starts putting you in the mindset of, I should be building something that's modular here so that I can test it. So generally, I think this idea of specify first, maybe I would say, is a good idea. It forces you to slow down and think about how it behaves. But often you might be approaching code that already exists. Okay, then it's too late. You can't do test-driven development on that. You just have to write some tests to try and capture something about it. I feel like there was something else I was going to say. Oh yeah, where are my slides on this? I think I might have moved them. So... yeah, then somehow got moved to it. Okay, so a last thing is what's called code coverage. How do we understand the extent to which our tests cover the code base? And here, this is based on the idea of kind of control flow paths or like lines of code. Do I have tests that test every line of code or every possible kind of branch in my code base, and what percentage of that is hit? So this is an analysis that can be done for us. We can ask PyTest how well does my code cover the space of my program. So we can run this as an extension to PyTest. There are a lot of extensions to PyTest, but this is one of them. It's called PyTest Cov. So I could check all of the tests and do --cov and specify over what set of code I want to check the coverage. So I'm going to do the source directory, and we get some information out here that tells us their coverage. So our helpers file, that's looking good. That's got 100% coverage. Our observation file has 92. Our energy balance is 85, and these ones have 0. We can get more information out of this as well. We can find out where. I've forgotten the command, but it's on the slide. --cov report term missing. Okay. Which is going to tell us which lines we failed to test. Okay, so we don't have any tests for lines 57 to 61. Let's have a look at that. Okay, so this is an energy out function. We didn't actually do anything about that. So we could go and write some tests for that now to increase the coverage. Now, I will again put a caution in here that this can sometimes be a bit misleading. It's not telling us about input space coverage. So this is about control flow, about which lines have been will get executed during the tests, but it doesn't tell us about the data flow, about that kind of data input space. If I just test the square function with, oh, does square of 0 equal 0, it's going to give me 100% code coverage because I tested that function, but maybe this square function isn't really what I intended. Maybe it's always returns 0, and so I haven't really tested the input space that I was interested in. So it goes back to our specification. What do I actually care about here? What do I want to specify? So this is not a data coverage. This is a control flow coverage. It's also sometimes misleading. Let's look at helpers. It says 100%. So I might be like, yes, the helpers thing is completely covered. Great. Let's look at what's in helpers. It has this linspace function, which is a standard function I just kind of replicated here, generates a list of evenly spaced numbers. So apparently that's tested. Great. Let's have a look at how it gets tested. Drop back to single. Let's look in our tests. Okay, so let me search for linspace inside of the test directory. Okay, I had a little test. I had some tests here. That's great. I was testing that. Let's take this out and run PyTest Cov again. Still 100%. That's weird. This was my only test of the linspace function, as far as I can see by looking at it. turns out that my smoke test happens to, which uses the plots. Those plots go and use linspace to kind of do like a how does temperature vary based on albedo. So they use linspace, but they never actually check anything about the actual output. This was a smoke test, basically just saying, did the plots get generated, yes or no? So it wasn't really a very good test of linspace. It was like a smoke test for linspace, I guess, but the coverage is saying 100%. So, you know, checking coverage is great. Higher coverage is good. 92, I might think, oh yeah, that's actually pretty decent. Or 100, great. But we have to think, what actually are those tests? So another word of caution. Okay, yeah, if you want to look at more examples, you can see here's another parameterize. I really didn't write very many. You could write a whole bunch more interesting tests there for linspace. That might be one of the exercises. So,
Question.
yes.
What is control group? Is it just methods? That's it.
Yeah. So I didn't explain that. So the control flow in a program is basically where the computer is going when it's executing your code. So one control flow path in this code is, if this is true, then we go over here. But there is another control flow path, which is if this is false, we don't go there and we go somewhere else. So those are like, if we think of that as almost like a decision tree of where could the program go, there's a true case and there's a false case here. We need to make sure that we're checking all of those branches. And essentially, most coverage tools basically report it in terms of lines of code. Basically, have we covered all the lines of code? Is another way of saying it. Any other questions? So I'll say one more thing before we come into land. This is what's going to happen in session 2. You're going to sit down and work through the exercises on unit tests for a bit. We're going to look at these other testing concepts and then have some more exercise time. But if you don't come, do try them later. I want to end with property-based tests in case you don't come to part 2, because this is one of the coolest things, I think, in testing, but it's not very well known in the sciences. So the idea with a property-based test is, rather than us thinking of all of these specific input-output things, which takes a lot of time and maybe you just don't think of some important cases, property-based tests is instead, the idea is to think of a very general property that we want to be true about our code, and then have it automatically tested for us by a framework generating lots of possible inputs. So let's say I'm making a list library function and I write the reverse function, like the reverse is a list. Don't know why I'm doing that, but I might be doing that. And I can think of some properties that I want to hold. For example, the reverse of a list should always be equal to the original list. So it's like a general property I could describe on any input string or list. Doing reverse should give me back the same thing. Now I could go and do a parameterized version of this where I say, okay, what about the empty list? What about a list with 1? What about a list with 1, 2, 2, 1, and so on? And I have to write a bunch of test cases. But with a property-based test, what you do is you give this function to your framework, and it will automatically generate you loads and loads and loads of random inputs and test this function on them. So you have this this kind of property function, gets plugged into this generator. Typically, they generate 100 possible values, and it runs it on those values. And it's really nice because it will systematically specialize, but also randomize. So it will generate you things that you might not have thought of. And my experience is it often generates things you have never thought of, like strange corner cases. And it does it, you don't have to write down those 100 cases. It does it automatically for you. So all you write down is this, and the framework looks at this and says, okay, I'm going to generate you 100 possible inputs for this and try it out on every single one. And it's an incredibly powerful technique, but there's a kind of artistry to then come up with what are good properties. And that is what we'll talk about in session 2. Okay, so that's the end. Let's get some coffee. Thanks.